Hello.
Good morning.
Hi, good morning.
I'm not aware who's supposed to be giving the presentation here.
I need to check that.
Okay, please do. Hello.
Yeah, I think it's Gugan Thope.
No, but I spoke to him and he was telling me that Mr. Bhatnagar, Professor Bhatnagar was supposed to continue where he left out.
Okay, then he will join possibly.
Would you contact him, please?
Just a minute, I don't have his number. So okay, I will ask.
I've tried to call Professor Bhatnagar, but his phone is switched off.
Okay, then maybe we should wait. He will join.
Sure. Just wanted to give you the feedback. I will put his number on the chat.
Okay, yeah, thank
Do you have access to the consolidated sheet, by the way?
you. No, I don't have.
Okay. I have put the number on the chat for you also.
Yeah, thanks. I got that. So I will also try to call him.
Yes, please. Thank you.
I talked to him. He's joining now.
Great. Thank you.
Yeah.
All right, so let's get started. So we will be continuing from where we left last time in the previous lecture. And essentially what we did was to talk a little bit about reinforcement learning, what it is and so on. And then, we started discussion on Markov decision processes. So it turns out that it is important to talk about or understand Markov decision processes in order to fundamentally understand what reinforcement learning is. Because you can view Markov decision process as the pillars on which reinforcement learning sits. Okay, so it's actually an important, therefore a fundamental topic. So in order to understand what it is, and we saw there is these notions of what we call as the Bellman equation for optimality and so on. And then we talked about numerical procedures for solution to the Bellman equation. Now it turns out that all of this requires knowledge of the transition probabilities. Transition probabilities, or what we also call is referred to as system model, is something that is totally fundamental to the solution techniques that are involved when we talk about solutions to Markov decision process. In most real life systems, however, we will in fact never have access to transition probabilities. Okay, so then the question is, well, can we estimate transition probabilities? And then once we estimate transition probabilities, can we go about applying the same numerical techniques that we learned of value iteration and policy iteration? You can do that. I mean, you can actually try and estimate them based on the data that you observe in terms of the state's actions, costs, or rewards in the next states. But then that's again going to be computationally expensive simply because most real life systems will have enormous number of states. Okay, so it's not that these will be systems with 5 states or 10 states or 100 states that are manageable computationally, but they will have like 10 power 100 states, 10 power 1000 states. What do you do in such cases? I mean, you can't really go about finding transition probabilities for every state action tuple and so on. So the second possibility is we directly try and estimate J mu. What was J mu? J mu was the value function. Value function we saw as an extremely crucial quantity to it, and what it tells us is it in a sense gives us the value of a state under a given policy. It tells you how good that state is. Now, as a decision maker, your task is to decide on an action that takes you to the state with the highest value. So actions are chosen based on values of states in general. But the problem is you don't know the values. I mean, no one tells you what the value of a state is. If the values have to be estimated. Values have to be estimated based on the costs or rewards that you obtain from a given state and the action that you choose in that state. Okay, so this is basically therefore a dual problem. You need to estimate the values, but in order to estimate the values, you need to play out actions, and then actions should be played out based on the value estimate. So it's basically that sort of thing that keeps going back and forth. Okay, so the key is if you really have good idea of what the values of states are, then decision making is easy. I mean, you can really figure out which states to go into and what are the likely actions that will lead you in possibly the shortest amount of time to such states. Okay, so there is this class of approaches that go under the name of Monte Carlo techniques that we'll now be talking about. So here the idea is that you don't have transition probabilities, but what you have access to is the following: that you can possibly run sample trajectories and of your system and collect data in the form of state, action, cost, next state tuples. So these are 4 tuples of the state, the action, the cost that you obtain. Again, that's a sample cost, the single stage cost that you obtain there, and then the next state. Uh, so let's consider, suppose we have, let's say, the kth such trajectory, where all actions are chosen according to a certain policy mu. So the superscript indicates the trajectory index. Okay, so kth trajectory means I'll put all k's on top. And then this is the initial state sk0, the action you choose, the cost you incur, and then the next state and the action you choose there, the cost you incur, and so on until termination. Let's assume it's an episodic task or a shortest path problem. where there is a termination that happens when the time is capital T. T is random in general. Okay, so if you have such a trajectory, then an estimate of J mu of I, assuming that Sk0 is I is the initial state, would be the sum of all these costs. I mean, so you sum gk0, gk1, all the way up to gkt minus 1. Okay, so that would essentially be a sample of J mu of I if the initial state is I. Okay, if you were in the discounted cost problem, such a sample would be obtained in a similar manner, except that you discount all of these things. And of course, in this case, there is no termination time, but ultimately you will still need to, have some sense of termination. I mean, you will have to ultimately look for a termination instant. So let's say capital T is a priori, you decide what time that would be and just fix it at that. Okay, so now the thing is that the same trajectory can be used to collect multiple samples. It's not as though this trajectory will give you only one sample corresponding to Sk0 equals I, which means this would not give you a sample of J mu of I. It can give you samples of the cost that you incur in the next state and the next state as well. So, for instance, in this case, GK1 plus all the way up to GKT minus 1 would be a sample of J mu J if the next state was J. Okay. So from the same trajectory, you can collect multiple samples of the value functions of the various states that occur during the course of a trajectory. And in general, what happens is that a state can be visited multiple times on the same trajectory. So there are two approaches that exist and that differ in the way the samples are collected. The first approach is that you collect samples only during the first visit of a certain state on a trajectory, which is what we call as the first visit method. The other approach is whenever you visit a particular state, you collect a sample. Okay, so that is what we refer to as the every visit method. I'll illustrate that by an example. But essentially, these are sort of what we are talking about. These are kind of the estimates that we have. So on let's say the kth trajectory, we collect this estimate. So which is the cost to go on the. So this would correspond to the cost to go on the mth visit to state I on the kth trajectory. So that's why we refer to it as CI. MKI represents the state from where you're starting to collect your cost samples. M is the mth time that state I is being visited on this kth trajectory. And that is basically denoted in this manner. This is just the sum of cost starting from that point, the mth visit to state I, okay, and until termination on that particular trajectory. So if you run a total of capital K trajectories, then you sum over all these quantities and divide by the total number of times that this state I has been visited on all of these trajectories. So that would correspond to the Monte Carlo every visit method. In the first visit method, you do something similar, except that you are only recording the first visits to a particular state. You are only collecting samples from then on. For the subsequent visits on a trajectory for the same state, you just ignore that sample. Okay, you don't just record that. So in that sense, would simply be a sample average of this quantity, which would correspond to the sum of costs as on a given trajectory whenever a particular state is visited the first time thereon. Okay, so here's an example to illustrate what I just said. So let's say we look at a kth trajectory, and this kth, these circles denote the states, and the states are 1, 2. So on this path, what we encounter is state 1 to begin with, and then state 2 follows. After state 2 comes state 1 again, and then it's followed by the terminal state, which is state 0. And these are the costs that are represented: 2 on this transition, 1 on this transition, 3 on this transition. So the every visit method would sort of look at two estimates of state 1. The first estimate would correspond to 2 plus 1 plus 3, which is 6. And then the second estimate would correspond to just 3, that is for state 1. Because state 1 is being visited twice. State 2 is being visited once on this trajectory. So the estimate there would be 4, 1 plus 3. The every visit method would not count this at all, would not count the second estimate for state 1. It would simply count the estimate starting in state 1 because state 1 is visited the first time here, and then state 2 is visited for the first time here. So it just records 2 of these estimates, one corresponding to state 1 and the other corresponding to state 2. But in general, it turns out that both approaches are seen to converge to J mu as k goes to infinity. J mu is again, by the way, the true value function. Now, the drawbacks here with these approaches are that both of these methods, they are non-incremental, and therefore they in general would not provide you with real-time solutions, because the fact that you need to generate the entire trajectory before you start collecting samples. And trajectory generation can be an arduous task. I mean, it can take an extremely long time, particularly in real life systems where the number of states is humongous, and if you have a certain goal state or a set of goal states, I mean, it may take an extremely long time to reach there. And so trajectories in general would be extremely large. And then these methods are going to take enormously long even to generate a single trajectory. Because all said and done, the samples are going to be collected only when trajectories have been generated. Okay, so that's a problem. So on the other hand, what we would like to do is to look at incremental approaches that would update the value function as soon as a data sample arrives. Okay, so towards this end, actually, stochastic approximation helps us. One of the ways in which it helps us is to sort of do things incrementally update these estimates. So for instance, if you look at the following, let's say x1, x2, x3 is an IID sequence of random variables with mean mu, and mu k is the sample average, which is obtained in this manner. And as Gugan had also talked about in his lecture, you can sort of recursively generate mu k. So mu k plus 1 would depend on mu k, and you can see that this is how you can sort of obtain this. Instead of having to record and store all of these samples of x1, x2, x3, and so on as they become available, you can sort of keep just 2 samples, 2 estimates, one of mu k and one of xk plus 1. And every time a new sample of xk is observed, you just record that and then update the mu k to a new mu k. Let's call that as mu k plus 1. So this procedure would actually help us in that manner, and that's something that we will apply as well. So okay, so one way to view Monte Carlo methods is the following: that instead of doing the sample average the way we described it, you can sort of do it incrementally in this manner, as was explained in the previous slide. As soon as you have a trajectory estimate, the sample estimate of the cost to go from state I collected on the kth trajectory, you just plug that in and then update j mu k, j hat mu k of I, which is an estimate of j mu k of I. And you keep repeating it so the point is that if you have more number of trajectories, this estimate gets better and better. And we know that as k goes to infinity, j hat mu k of I would converge ultimately to j mu of I. But even though this is a stochastic approximation update, the point is that you are still not making use of on data samples as they become available online. You are still waiting for the entire trajectory to get over before you do this update. Okay, so what one would ideally want to do is to update these your samples, obtain sample updates as soon as data samples get available. And that's the approach that goes under the name of temporal difference learning that I am going to be talking about now. So the idea here is that, let's say we just collect this equation on the previous slide, and this is what I have rewritten. This is what it is. And now what we'll do is we'll just massage this a little bit. So let's say we look at what exactly CI1K is. CI1K is just this sum of the single stage costs that one encounters on the trajectory K when you are starting in state I, okay, or let's say when state I is visited for the first time on that trajectory. From then on, this is what it is. Okay, so this is simply CI1K has been rewritten here. What I'll do is I'll not write it as a summation, I'll write it as a sum of individual terms, and that's what we have done. And then there is minus j mu hat k of I. So I'll add and subtract quantities. I'll add j hat mu k of skt plus 1. I'll subtract this. So similarly, I'll add this. I'll subtract it on the next thing with this quantity j hat mu k skt plus 2. And finally, I'll add j hat mu k skt minus 1 and I'll subtract this. There's this additional term j hat mu k skt, but then this, since capital T is a termination instant, this is actually 0. Okay, so I can just add and subtract. I can just add this term because it's just the value of this is 0 anyway. Now we understand that these can be viewed as temporal difference terms. So let's write this out in the following manner. So we can write this update as j hat mu k plus 1 of I is j hat mu k of I plus 1 by k plus 1 into the sum of all these what we call as temporal difference terms, and that is denoted in this manner as DKL. So what is DKL? It's the sum of the single stage cost and the estimate of the cost to go from the next state onwards minus the estimate of the cost to go from the current state. So these are what we call as temporal difference errors. Okay, so this is essentially an estimate of j hat mu k of skt that gets updated in this manner by collecting together the average of the so sort of the sum of the temporal difference terms. Okay, so what exactly is this? So suppose for a moment that instead of use a different step size, let's say I use a step size alpha. Of course, I'm not saying what alpha is for a moment. Let's say it is some alpha, and let's say we. So if you see what this is, so suppose as so you are starting at time 0. So j hat mu of S0 would then be j hat, the new j hat mu of S0 would be the old j hat mu of S0 plus alpha times the sum of all of these quantities, d0 plus d1 up to dt minus 1. Then you go into the next instant, then at the next instant, the state is S1. So j hat mu of S1 would be the new one would be the old one plus alpha times, the sum of all of these quantities is d1, d2, and so on up to dt minus 1, and you collect these samples in this manner. Now, the thing to observe is that d0 is something that appears only in the first equation. d1 appears in the first two equations, d2 appears in the first three equations, and so on. Okay, so that's the way it progresses. So d1, if you use d1, d1 is used in the update of j hat mu of S0 and j hat mu of S1, and therefore, if I mean, it's clear that you can write these equations in this manner, that you can sort of update them as j hat mu of SL is updated as j hat mu of SL plus alpha dt, where t lies between L plus 1 up to capital T minus 1. Capital T again is your termination instant. So the point is that as soon as a transition from ST to ST plus 1 happens, you know what dt is, and therefore one can update j hat mu almost immediately. Okay, so you don't have to really wait for the end of the trajectory. You go on updating all these estimates as soon as these transitions become available to you. Now, okay, so this is essentially what it is. So this is the standard form. Now, okay, so now let's look at this. Let's stare at this for a moment. Now, the point is that if you recall what the Bellman equation for a given policy was, the Bellman equation said that it was, okay, so for a given policy, J mu of I constitutes the value function corresponding to policy mu when you are starting off in state I. So that is essentially the expected value of the single stage cost plus the cost to go from the next state onwards under, of course, the same policy mu. Now, the point is that you can have an alternative form of the Bellman equation, wherein instead of a one-step equation such as this, you say that I'll look at the sum of the first two single stage costs and then the cost to go from the second stage onwards instead of the next stage. Alternatively, you can say I can look at the sum of the first three stages, the cost of sum of the single stage costs of the first three stages, and then the cost to go from the third stage onwards. In general, you can look at the sum of the first m stages, costs of the first m stages, and then the cost to go from the m plus first stage onwards. Okay, so in general, it's not clear, I mean, which form of the Bellman equation to use. So what he suggested is, let's say we weigh all these Bellman equations by a factor lambda. So one thing is, well, J mu of ST can be rewritten in this manner. So lambda is something that lies between 0 and 1. So let's say that it's less than 1 for a moment. So then essentially this equation will be true. And therefore, what you can do is you can, because you have J mu of ST here, and J mu, instead of J mu of ST, you can plug in the M-step Bellman equation. And once you do that, this is what happens. I mean, you can bring in the M-step Bellman equation. So the M-step Bellman equation is weighed in by a factor of lambda power n. And Nm goes from 0 to infinity. Okay, and then you are multiplying all of this with 1 minus lambda, which is a normalizing factor. And if you sort of, sort of look at this equation and the reorganized terms and so on, this is what happens. I mean, so ultimately what you get is J mu of ST ends up being of this form. And what it means is that if you were to look at a stochastic approximation version of what we call as the TD lambda algorithm, this is what happens. I mean, so you can update J hat mu of ST in this manner that the new J hat mu of ST is the old one, old J hat mu of ST, plus a step size alpha times summation L equals T to infinity of lambda power L minus T dl. Okay, dl is of course constitutes the step size. Let's look at certain cases. So in general, of course, lambda can be 1 as well. I mean, one can prove that with lambda equals 1, you can still have a version of the TD lambda algorithm. Let's look at the corner cases. What happens when lambda is 0 and what happens when lambda is 1. So when lambda is 0, we call it the TD0 algorithm. And this has the following form. So if you plug in lambda equals 0 here, so it will, only the first term will count, because then the term that corresponds to Q equals T. So this will be 0 power 0, which we take as 1. So this is then dt is what comes in. So what you get is J hat mu of ST is updated like this, that the new J hat mu of ST is the old J hat mu of ST plus the step size alpha times dt. Dt is like the temporal difference term, okay, that you obtain. So this is actually a fully online algorithm. Okay, so clearly, as soon as a data sample arrives, you just go on updating, you update the value of the state that is visited at that particular instant. Okay, so that's and then you move to another state, you update the value of the next state as soon as the next data sample arrives, and so on. Okay, so that's how the TD0 algorithm would work. Consider the other corner case wherein lambda is 1. Okay, so when lambda is 1, all of these terms are 1. Okay, so what you get is then J hat mu of ST would be the new J hat mu of ST would be the old one plus alpha times the sum of all of these temporal difference terms. But then the sum of all of the temporal difference terms, we see that it just amounts to the sum of the costs that you encounter on a given trajectory. But then that's the same as the Monte Carlo return, right? I mean, so TD1 algorithm is the same as Monte Carlo algorithm. You just collect together all the, so you need to wait for the entire trajectory to play out. And then you collect together all the sum over all the costs that you encounter on the trajectory. Use those in your update rule. So that's basically just TD1. That's basically just Monte Carlo. Okay, so TD1 is Monte Carlo. TD0 is a fully online update. But then by playing around with lambda, lambda could be any parameter between 0 and 1. You're sort of playing between these two kind of algorithms, a fully online update rule versus a fully Monte Carlo update. Okay, next let me talk about what we call as the Q-Bellman equation. And this is also something that is fundamentally important, and we'll see why. Okay, so recall what the Bellman equation corresponds to. The Bellman equation is the following: that for every state I belonging to S, V star of I, which is the value function, value corresponding to state I, is the minimum over all actions A in A of I. Basically this is the expected value of the single stage cost plus discount factor, assuming we are in the discounted cost setting for a moment, times the value of the next state. Okay, so this is essentially what it is. Sorry, there should be a closing bracket here which I missed. Now let's say I define Q values in the following manner, that forget about this minimum, whatever is on the right hand side without the minimum, I call that. Now this thing that is without the minimum outside this summation, would be a function of the current state I as well as the action A. So which is so this Q star has two arguments in it, the state and the action. Okay, so let's say Q star of IA is this. Then clearly V star of I will be the minimum over A in AI of Q star of I comma A. Okay, so one could have plugged in minimum over A in AI of Q star of J comma B or something here. Now the point is, if we look at this equation wherein Q star of IA is defined and then plug in this quantity inside, what we get is this equation, which is Q star of IA is the sum over J of PAIJ of this entire Wellman of the picture. And observe that that would also be a contraction because of the fact that there's a gamma, which is the discount factor. And as a result, you will, by the Banach fixed point theorem, you will encounter a fixed point, a unique fixed point, Q star. And so there will be a unique solution to this the Q-Bellman equation. Now one can derive a value iteration based procedure for solving this Q-Bellman equation, which would essentially amount to this. You start off with an initial guess Q0 of IA for all IA tuples, and then go on updating Qn in this manner. And we know that as n goes to infinity, Qn would converge to a Q star. Now again, the point is, if we don't know PAIJ, which are the transition probabilities, then essentially one can basically apply stochastic approximation. And the reason why we are able to apply stochastic approximation is because of the fact that the minimum which was here in the Bellman equation just to the right of the equality and before the expectation was taken has now moved inside, and that helps us because now the expectation is outside. And if we don't know the expectation, you can just collect samples and then use them in a stochastic update rule, and the expectation would almost come for free asymptotically. And that's essentially what happens. So this is the Q-learning algorithm, which was developed by Watkins and Dayan in this paper in 1992. And what they suggested was you make use of these data samples as they become available, and just run this algorithm. And as n goes to infinity, you can see that this algorithm will converge to the optimal state action value function, which is Q star of Sn, S comma A. Now the point is that one thing is, as you run this algorithm, one may ask the question, how do you select AN? There are various ways in which you can select AN. One of what is suggested in the book by, let's say, Sutton and Bartow, is that you use what they call as an epsilon greedy policy, which means that AN is selected to be the greedy action, the action that minimizes Q of SNU as it becomes available. With probability 1 minus epsilon, you select the best action, the current estimate of the best action. And a random action you select with probability epsilon, and this helps us in exploring actions that have not been explored previously. And also because otherwise this would lead to biases that would result from the fact that you sort of put all your weights on a certain action, and that may end up not being optimal. Okay, so you need to explore. So there's one possible exploration strategy, but in general, you could select any actions according to any policy that assigns a positive probability to all possible actions. Okay, so as long as you are doing this exploration, that's fine. I mean, see, the point is that inside this quantity, there's this minimization. So this is the greedy step that you are doing anyway. Okay, so this is actually crucial here. But outside of it, the way you select these actions as soon as a state is visited could have been according to any policy. Okay, and so which basically means, so the point is this algorithm will converge only provided all these state action tuples have been visited an infinite number of times. And that will happen only provided all these actions are selected with a positive probability in every single state that you encounter. Otherwise, you won't get convergence. Okay, so that's important to keep in mind. Now, the point is that if we look at another problem that one encounters with these algorithms, is the fact that if you have in the most real life systems, the number of states that one encounters is going to be humongous. As I said, in many applications, one might even encounter states that are of the order of 10 power 100 and so on. So for instance, if you think of let's say communication networks or traffic networks and so forth, wherein the moment you add more nodes into your system, you add a dimension actually to the state, or maybe multiple dimensions to the state. And the more dimensions you add to the states itself, the set of states starts growing exponentially. And that is how you can encounter these large number of states. I mean, if you were to control, let's say, a communication network or a vehicular traffic network and so on. Okay, so in such systems, it really makes no sense to sort of think of what would be the value function of state, maybe n as opposed to state n plus 1, okay, for any n. And essentially record all of that and do all this huge amount of computation. Because all said and done, I mean, it may not even make much sense to do all that, right? And so what we essentially end up doing is to approximate the value function using a parameterized class of functions. And one way to parameterize it is to use a linear function approximation architecture, wherein you parameterize, let's say, the Q values in this manner. That's theta transpose sigma IA. It is linear in theta, the parameter theta. And these sigma IA are what we call as feature vectors corresponding to the state action tuple I, comma A. But then this sigma IA need not be linear. I mean, it's not linear. It's not necessarily linear in IA. I mean, it could be a polynomial. It could be anything. I mean, it could be highly nonlinear function as well. It's linear. It's when we say linear approximation architecture, I only mean linear in the parameter. Okay, so that's about it. Now the point is, if you are parameterizing it in this manner or in some other manner, maybe you parameterize it as a neural network based using a neural network architecture and so on, and then you look at the associated parameters of that correspond to the weights of the various layers in the neural network. So then all of that put together would be the tunable d hat dimension, some d hat dimensional parameter that will need to be updated then in order to get to the best estimate of QIA. So using function approximation, one would derive, I mean, there's some algorithm like this, wherein the sigma Sn of, so Cn corresponds to the step size of the learning rate. Sigma Sn of An, sigma Sn An would correspond to the feature vector corresponding to this Sn An tuple. I mean, the Sn An, the state action tuple. The feature vector. Well, what is this feature vector? I mean, if you take the gradient of QIA, that would actually be with respect to theta, that would be sigma IA. And so this algorithm can actually be derived by using the Bellman error squared laws of objective, and then you take the gradient of the other, then essentially you can sort of see that this is how it will end up being. But the problem with this algorithm is it does not converge. I mean, it's many times diverges, and the reason is it suffers. I mean, Q learning in general suffers from what we call as the off policy problem. And the reason is that the way in which the target policy is sampled, the target policy is actually greedy. I mean, it's actually this minimization over all actions that are feasible in state Sn plus 1. So it's a greedy policy that you select, but then the behavior policy that is being used to select the actions in the particular state, whose state action tuple is getting updated, is actually it's in general not greedy. So that results in this difference in the behavior versus the target policy, and that results in this off policy problem. And there's a lot of literature around the non-convergence of Q learning in general. Now the point is that if you were to replace this, if you just remove this minimum, let's say, and you just select the action V according to a given policy, and let's say you perform these updates, wherein the action AN is again chosen according to the same policy, according to which you choose this action V in state Sn plus 1, then that would correspond to basically the TD algorithm. I mean, it would just be the TD0 algorithm with function approximation. I mean, there's nothing special about it. I mean, you would just end up finding the value function or the value function parameter or the estimate of that using the TD algorithm itself. But the moment you do this kind of a thing, you sort of you bring in this minimum over all actions and so on, then it becomes the Q learning version. And this minimum actually makes it a highly nonlinear update. And because of this off policy problem, there is non-convergence that one observes. There's another class of approaches that goes under the name of what we call as policy-based methods. I mean, we looked at what we call as value function-based approaches. Now, what I'll be talking about also is these policy-based methods. So in value function-based approaches, what we did was to approximate the value function using a parameterized family of functions. Maybe the parameterization could be over the value function. We parameterize it using some parameter phi, or q, the q value function using some other parameter. Let's say we call that as phi as well. Now, the policy that was being used was then generated using these parameterized value functions. But in policy-based methods, what we do is we parameterize the policy using a weight vector, a certain weight vector, let's call that as theta. Okay, so we parameterize, instead of the value function, we parameterize the policy. Okay, so the policy, what is the policy? What does the policy tell us? I mean, it gives us the probability of picking action A in state S. And let's say these probabilities depend on a certain parameter theta. Now, as compared to value-based methods, policy-based methods have certain advantages. I mean, they typically work with randomized policies that allow, therefore, for the use of gradient-based approaches, as against value-based methods that would normally work only with deterministic policies. And in general, these have better convergence properties. They are more effective in high dimensional or continuous action spaces. For example, let's say an example could be of learning, controlling the steering wheel in autonomous driving. They can learn stochastic policies. I mean, value-based methods would invariably learn deterministic policies. I mean, value policy-based methods, and on the other hand, will learn in general stochastic policies. And the resulting optimization problem invariably involves some form of stochastic optimization. And one can largely use things like neural networks to find the optimal policy. A disadvantage, however, is that evaluating a policy is typically inefficient, and it can result in high variance. Okay, here is so there are a class of approaches that go under the name of policy gradient methods. So in the average cost setting, let's say I'll recall this. I'll just put this slide out. So let's say we assume that the policy is parameterized, as I have been just mentioning. And the goal is to find, so if I parameterize the policy, then the goal would be to find the optimal parameter, which would then correspond to the optimal policy within your class of policies. Okay, so the goal is to find a theta star that minimizes, let's say, lambda pi. Lambda pi is the average cost. Okay, so now pi is the policy, pi depends on the parameter. So that's the gives rise to this relationship of the average cost on this parameter theta, because pi is a function of theta. Okay, so let's assume that pi theta of IA is continuously differentiable in theta. Okay, so this is the policy that continuously, okay, so it's a continuously differentiable function of theta for any state I and for any action A. So here is this theorem that is called that's now famously called the policy gradient theorem. And it's been independently derived by several authors. I mean, so there is this paper by Marbach and Sitsiklis in 2001, and Sutton et al. In 2000, by Baxter and Bartlett in 2001. And then there are others, Shiren Chow et al., I think in 98 or something like that. I mean, even before 98, this result was known in some form or the other. So it has been independently derived by all these people. And what it says is the following, that if we take the gradient of the average cost, this actually has this form. What does it say? It has this quantity d pi I. So d pi I is the stationary distribution of the Markov chain under policy pi. So we assume, of course, that the underlying Markov chain is ergodic and so on under any given policy. So if you start off your algorithm, I mean, you will settle into the stationary distribution corresponding to a given policy. And so note that there was a gradient on theta. And this gradient, the important thing about this result is that this gradient goes and sits on this pi. Now pi is something that you have decided to use. Okay, pi, of course, we said that pi should be continuously differentiable, but then that's in your hands. I mean, you can really decide on what pi to use. So finding the gradient is not at all difficult once you have decided on the functional form of pi, because that's in your hands. I mean, it's not something that you will have difficulty in deciding on. The important thing to note is that this gradient does not sit either on d pi, it does not sit either also on q pi. And that's the important thing. Then q pi ia again is the q value estimate corresponding to the state action tuple. Okay, so there's another form of the policy gradient theorem which introduces a baseline. So everything else is the same except that one could have a B of I as well here. And what is this B of I? What does it do? Well, what it does is that if you look at the sum over I in S of d pi I into the sum over A in A of I of grad theta pi I A into B of I, then you can pull this grad theta out of this summation. And if you do that, then it's just some grad theta of this summation over A and A of I of pi I. And B of I can be taken out because B of I does not depend on action. Now this sum over A of pi IA is 1, and therefore the gradient of this is 0. And so this quantity actually contributes nothing. And so there's just something that we have just included. Now one may ask, why have we included if it contributes nothing? Well, the reason why many times we use this baseline function is that through a judicious choice of the baseline function, one can actually reduce the variance of the gradient estimator. Okay, and it turns out that the value function under the given policy is actually a good estimate, good baseline function to use in such estimators. Okay. So let's assume that we have pi IA that have this functional form. That let's the parameterized Boltzmann distribution, where phi IA are like some state action features, and theta is then the associated parameters. So pi depends on theta, and it depends in this on it in this manner. Now, if I take the gradient of with respect to theta of pi IA, you can see that this turns out to be this. So it is pi IA itself times pi IA minus the sum over B in A of I of pi IB phi IB. And let's call whatever is inside this bracket to be psi IA, which is another state action feature. So this would then correspond to pi IA psi IA. And the thing to note is that if I sum over all actions pi IA psi IA, then that would actually be 0. Right, I mean, so this is something that is important to note. So if I sum over all actions A of pi IA psi IA, so then this term would have sum over all actions pi IA phi IA, and then this would be the same as it is, and then they will cancel away and you get 0. Okay. So in general, features psi IA that are derived from pi IA in this manner, that okay, so what is psi IA? What is the relationship to the gradient? I mean, so if I write gradient pi IA divided by pi IA, that is psi IA, but then gradient pi IA by pi IA is nothing but gradient of log pi IA. So I can write psi IA as grad log pi IA, and such features that are obtained from the policy in this manner, that you take the gradient of the log of the policy, they are called as compatible features, because they satisfy this property that is useful in some of these calculations, that the sum over all actions of pi IA psi IA is actually 0. Based on this, there is this algorithm that goes under the name of reinforced policy gradient algorithm. So which is a stochastic approximation counterpart of whatever we discussed. I mean, so here we use the policy gradient theorem in the following form. So note that the policy gradient theorem tells us that we have the gradient of lambda pi, which is this. Now the point is we don't know d pi of I, which is a stationary distribution of the Markov chain. We can certainly find this grad theta pi IA. And we need to estimate q pi IA. No one tells you what q pi IA is a priori. You need to estimate it. So we'll estimate that using, the sum of costs on a sample trajectory. And if you do that and multiply it with the gradient of the log pi theta IA, multiply it with a step size and add it to the old update of theta to get a new update. Where CT is basically, as I said, the sum of these costs on the trajectory, which we also call as the return, the cost to return on a trajectory. Then one can show using techniques from stochastic approximation that this algorithm will converge to a theta star, for which ultimately what will happen is that it will converge to a theta star for which lambda pi theta star, the gradient of lambda pi theta star, lambda pi theta evaluated at theta equals theta star should be 0. Okay, so ultimately it gives you a local minimum of the cost, of the average cost, okay, with respect to your parameter theta. So this algorithm is what we call as the reinforced policy gradient algorithm, but again, it's a Monte Carlo based technique. One could use a what we call as a reinforced with a baseline algorithm as well instead. So instead of the usual algorithm, you can subtract an estimate of the value function, and instead of CT, you can look at the sum of the single stage cost, and then gamma times an estimate of the value function of the next state, which would depend on another parameter W, but then of course this W is a value parameter that will have to be estimated separately. Okay, so the idea here is, of course, instead of CT, which is, as I said, the sum of cost on a trajectory, you replace that with the sum of the single stage cost and the discount factor times an estimate of the value function of the next state. But again, it depends on this is a value function parameter. Now, the value function parameter I have not said here as to how that has to be estimated. Okay, so it will require its separate recursion. And this gives rise to what we call as actor critic algorithms, and I'll briefly probably touch upon these actor critic algorithms if we get time. But essentially, this is what it is. I mean, one has actually policy gradient theorems for discounted cost as well, but in the discounted cost setting, it turns out to be a problem. It turns out to be somewhat problematic for the following reason. So if you look at the discounted cost, which we denote as, let's say, rho pi, as this, then if you take the gradient of rho pi, this turns out to be something like this. Okay, it is the sum over s of d pi s, which looks like exactly the same expression as that, but then d pi s is not the stationary distribution. In this case, d pi of s is the discounted sum of the occupation probabilities. Probabilities of finding, okay, so the probability of finding yourself in state S at any time. So if you are in state S at time 0, if you are in state S itself, which means that S is the same as S0 at time 0 itself, then you multiply it with 1. This probability, if you find yourself at time 10 in status, then that probability of finding yourself, probability that is 10 is as given that you started out in S0 and pi, that is multiplied with gamma power 10 and so on. And then you sum it over all of this, and that will be d pi of S. So as you can imagine, designing stochastic approximation algorithms in this setting of discounted cost policy gradient algorithms is not possible for this reason, because I mean, stochastic approximation algorithms are naturally, you can design them for the average cost setting, because ultimately when the parameter converges, you can see that, you recover the stationary distribution of the Markov process. I mean, it requires some certain amount of analysis, but which I am not touching upon in this tutorial. But you can actually see that one can obtain that quite naturally. It doesn't happen in the discounted cost setting, because all said and done, you can't recover something like this, I mean, d pi of s, which is quite a complicated thing to look at. And therefore, one needs to do something else. I mean, you can't really have stochastic approximation for policy gradient algorithms. Okay, this is something that I'll skip. I think I'm running out of time. So this is basically what this is suggesting is the following, that instead of doing a policy gradient type step, you might as well try to estimate the gradient of J mu in a different manner. The one way is to look at finite difference gradient estimates. So you run the algorithm for different values of the parameter theta that would in turn give rise to different values of the policy. And as you update your parameter, you have different policies to run with. So you can sort of keep on running these recursions for different values of theta and collecting estimates of the corresponding value function. And you go on finding gradient estimators in this manner. There is this class of approaches that goes under the name of simultaneous perturbation gradient estimation, stochastic approximation, wherein in the Kiefer alphabet scheme that is represented here, you require a large number of samples in general. I mean, you require 2D samples because the number of simulations becomes high for any d-dimensional parameter. Here you can do the same thing using just 2 simulations. I mean, of course, I'll not have time to get into the details. There's some work based on this that we did for the actor-critic algorithms, and which I'll skip for now. There's also one can talk about actor-critic for the long-run average reward setting with function approximation. This is essentially based on the paper that I had with Sutton, Gawamzadeh, and Lee, that was earlier. But of course, like, I don't have time to get into all of these details. Let me just skip them for a moment. Uh, and let me just, okay, I'll just give you a one slide primer on what actor critic methods are. Okay, so in general, you can think of actor critic algorithms as algorithms that that maintain two sets of parameter updates. There is the update that corresponds. So these are algorithms that mimic policy iteration in a sense. Now, policy iteration again is a numerical scheme that requires the knowledge of transition probabilities. Now, if you don't have access to transition probabilities, we have said we don't have access to the system model. And so what we do is we need still to estimate the value function corresponding to a given policy and then do the policy improvement step. So what these algorithms typically do is they will have two recursions running. One is what we call as the critic that updates the action value function parameters, which are W, and these are updated in this manner. Okay, where beta t is a certain learning rate that is being used, delta t is the temporal difference term, and phi of st is basically the feature vector corresponding to state st. So this is basically a temporal difference update that tries to update the value function parameters. And together with this, you run the actor update. So the actor is the policy improvement step. So it updates the policy parameter, which is theta. And in the actor update, you use this kind of a recursion which tries to do policy gradient. Okay, so assuming, of course, we are in the average cost setting in general, because you cannot use otherwise. As I said, policy gradients will not work in general with discounted cost settings. So let's say we are in the in the average cost setting in where you can actually use this kind of a recursion. Okay. Now, one thing, of course, which I have not mentioned is that typically in policy iteration algorithms, what you require is that the inner loop should converge before then update of the outer loop. The outer loop corresponds to the policy improvement step. The inner loop corresponds to the policy evaluation step. But in this kind of an algorithm, the way you write it, you decide on a beta t step size which is different from alpha t, and beta t so alpha t here would typically go to 0 at a rate faster than beta t does. I have not written down the technical conditions and so on, but roughly the idea is that if you in addition to the usual step size conditions, you require that alpha t by beta t should go to 0 as t goes to infinity. And once you ensure that, then actually you get the same effect as the policy improvement, as the policy iteration procedure would provide, which means that you have these two nested loops. In the inner loop, you do the policy improvement step, and in the outer loop, you do policy. So in the inner loop, you do policy evaluation, and in the outer loop, you do policy improvement. But then here the advantage is that you are running both of these together. So it's just this difference of step sizes that can actually help us understand these two in the nested kind of structure, as I explained in the policy iteration procedure. Because giving the details requires far more formal sort of a treatment, which we will not be able to cover in all of this. This cannot be done in a 2-hour tutorial. Let me just talk a little bit about this application, which might be of independent interest to some of you. So this application is of what we call as a cooperative energy exchange. So let's say here is there's a main grid that is supplying power over a distribution network to all these local loads and so on. And associated with these there are also microgrids that are available, so that cater to local loads. These could be loads in a building, let's say your department, or maybe then another department or set of departments, will have maybe another microgrid that is catering to the loads and so on. Now, typically what happens is that, when we talk of microgrids, they have a heterogeneous nature right from the manner in which electricity is generated. So electricity could be generated using wind farms or solar panels and so on. And also in the manner in which you store this energy that is generated, you could store it in batteries or capacitors and so forth. Now there is also, there is intermittency in the way energy gets generated. For instance, there is sunlight right now in Bangalore, and therefore solar panels would work very well, and they will be able to generate a good amount of, they will be able to generate a good amount of energy right now. But if it was raining, then of course, or it is night time, then certainly that would not happen. So there is enough randomness even in the manner, even in the energy generation process itself. Now, microgrids can typically, they can exchange energy locally instead of, requesting energy from the main grid. And the advantages are, you can also exchange this energy between microgrids. So one microgrid may be in need of some energy, and the neighboring microgrid might be able to provide that excess energy that the other microgrid is in need of. And by provide, I mean you can sell it off at a certain price and so on. Okay, so this would help typically satisfy demand and reduce reliance on the main grid. The challenges, however, are you require it requires handling both stochastic supply and demand. And as I said, this is largely due to intermittency of the generation, the energy generation itself. Uh, and also demand is stochastic anyway, right? I mean, so, yeah, so these are the various challenges. I mean, one of the challenges also is that you want to optimize grid performance using limited communication among microgrids. This is to ensure privacy and security concerns and so forth. Now, here is one model that we looked at. I mean, so this is a model wherein microgrids can buy or sell power from or to other microgrids as well as to the main grid. And then the goal is to decide how much of power to borrow or transfer. So if you are one microgrid, you may be willing to borrow power from the other microgrid if you are in need of power, or you may be willing to sell your extra power, additional power that you have generated to the neighboring microgrids. And then the state at time t for microgrid I can be described in this manner. T is the time and DIT signifies the excess powers or the deficit. I mean, you can think of NDIT as this quantity, which is basically the sum of the amount that you already have plus the amount that you generate minus the amount that is in terms of the demand. Now, this quantity can be both positive or negative, and if it is negative, it signifies deficit. If it is positive, it signifies excess power. And then, this PT would denote the price per unit energy that you want to sell your energy at, and JIT would be the set of what we call as ADL jobs. Now, ADL jobs is essentially these are what we call as activity of daily living jobs. So these are flexible capacity jobs. Now there may be so one can characterize demand as non-flexible and flexible. Now, for instance, if you are from your home, you want to drive to your office, and you know that you will be there in your office for a total of, let's say, 10 hours. And during these 10 hours, you might want to, you just turn on your washing machine, and you want your clothes to be, let's say, be ready by the time you reach back your home from your office after a duration of, let's say, 10 hours. Now, when that demand gets scheduled, whether it gets scheduled immediately as soon as you depart from your home, or whether it gets scheduled in a manner that by the time you reach home, your clothes are ready, essentially. So that basically is a flexible demand. Now, flexible demand is something that brings in some more complexity into the problem, because it allows for this flexibility. And so there is this demand that is non-flexible. You need to just cater to it right away. And then there is this demand that is flexible. So that's essentially that's something that we also took care of. So those are what we call as ADL jobs. And in this particular model, we assume that the prices are not changing. We just assume a constant price. Uh, and so the action is this tuple UT comma VT, where UT is the number of units that were to be borrowed, that you decide on borrowing or transferring to other microgrids or the main grid. And VT is the units of activities of daily living, I mean the flexible demand, jobs to be scheduled. And then this is a description of the single stage reward for microgrid I, where it depends pretty much on the flexible demand and the non. So this is the non-flexible demand component, this is the flexible demand component. And then this is the amount that you pay for the number of units that are borrowed or you receive in return for the number of units that you transfer. We used a multi-agent Q-learning algorithm for yeah, so we considered a few different models, the ADL sharing model and the non-ADL model, where the flexibility in demand scheduling is not there at all. I mean, so whenever a demand arises in this model, you just assume it needs to be met immediately. So that ADL demand is also then counted as a non-flexible demand. And then there's this greedy ADL model, wherein you just make a decision on selling power that is triggered only after the battery is full and demand is met, and so on. So here are some plots. Essentially, so what is observed is that the ADL sharing model seems to perform better than both the non-ADL model as well as the greedy ADL model in all these three. So this was a setting involving 3 microgrids, wherein this energy was getting shared and so on. The details are in this conference paper that appeared. Subsequently, what we also did was to look at this setting of dynamic pricing, where the state evolution is as before, but you also decide on the price to sell. So the ith microgrid decides the price Pi per unit to sell at time t. And then you apply this algorithm. I mean, the actions, so each microgrid requires this tuple of UIT, VIT, and PT. So PT is the additional thing that is being included now. And the algorithms are these dynamic pricing policy, right? And so this was these 3 decisions to be made. The amount of power to buy, sell, amounts of units of ADL job scheduling, and as well as the price to sell the excess energy. And then there's this constant pricing policy that involves 2 decisions, just the amount of power to buy or sell, and as well as the amount of units of ADL job scheduling. Price is just assumed fixed in this constant pricing policy. You don't change price as you move along here. And then there is this random exploration, just for the sake of completeness, we compared it with a random policy setting. Of course, we don't expect it to perform well. And that's what is observed here. So it turns out that the dynamic pricing policy, I mean, what is here is on the y-axis is the average rewards, on the x-axis is the number of iterations. And what we show on the y-axis is actually the running average of the rewards. So that's what is being shown. So eventually the dynamic pricing policy, I mean, the constant pricing policy is not so bad. I mean, ultimately the difference between these two is that you are still doing the optimization. In the constant pricing policy, you have just fixed your policy to be sort of heuristically decided over a few sets of policies that seems to be performing the best. But then the other decisions are still being made using an MTPs, I mean, using the same RL algorithm. The other actions, decisions on UIT and VIT are still being made using that. In the dynamic pricing model, in addition to finding the optimal UIT and VIT, the goal is also to find the optimal price. And so ultimately, it seemed to be doing better than the constant pricing policy. The random pricing policy was anyway not expected to do well. Here is these results, and when we compare, it turns out that the winning policy is 6 out of 8 times the dynamic pricing policy wins, and then 2 out of 8 times it's the constant pricing policy that seems to be better in these settings. Of course, yeah, so that's what it is. Yeah, there are several other approaches that one can talk about. We didn't cover things like non-incremental methods such as the LSTD, LSP. These are like least squares, temporal difference, least squares, policy evaluation, and so on. There's now a lot of work on reinforcement learning for constrained Markov decision process, wherein you have constraints in the you look at constraint functions as well, and then there are various algorithms that work with a host of Bellman error objectives. I mean, not just, I mean, there are various ways in which one can define this Bellman error. There's notions of Bellman error, projected Bellman error, and so forth. And then there are a lot of algorithms that have been derived based on these notions. Uh, we didn't talk a whole lot about off-policy algorithms and algorithms with nonlinear function approximation in particular. There are also approaches that use feature adaptation essentially on top of the usual, things like policy evaluation and policy improvement, like the actor predict schemes or the Q learning scheme and so on. You can also talk about what can we do to get the best features, and then you can define an objective function that would be optimized when the features have been selected in some manner. Uh, and then there are a whole lot of approaches that go under the name of that work for partially observed Markov decision process, wherein invariably you will not be able to have a full observation of the state, but maybe a function of that, or some part of the state would be hidden and so on. Okay, with that, I think these are the references that have been used in this tutorial. Yeah, if there are any questions, please let me know. We can discuss now. So we have ended. So this tutorial on foundations of stochastic approximation and reinforcement learning is now concluded. Yeah, so I am happy to take any questions if there are. Okay, I think I don't see any questions. So if there are no questions, shall we conclude? Okay, so thank you all. I guess there are no questions. So if you have any questions, if you have any questions later on, also you can just send me an email. Uh, uh, so my email ID is shalabh@iisc.ac.in. Please feel free to send me an email anytime. All right, so thank you all. So we can close this session now.